Okay, so we are on to question 7M4 on the second edition of Statistical Rethinking. And so I'll just read the question here verbatim. So what happens to the effective number of parameters as measured by PSIS or WAIC as a prior becomes more concentrated? Why? And perform some experiments if you are not sure. Okay, so let's kind of march through this a little bit. So remember that the effective number of parameters for PSIS and WAIC is the penalty term for these two measurements, okay? And even though this doesn't directly relate to the question, it will kind of get us into some of the answers, but why is the penalty term, or why is, I shouldn't say the penalty term, but why is the penalty associated with these two measurements called the effective number of parameters, okay? So let's try to answer that, and that will kind of back us into a more direct answer for the question. So all else being equal, models that have more parameters, okay, it's estimating more things, are going to be more flexible and therefore more capable of fitting data in general, just more capable of fitting data in general, all right? So the extent to which they're more capable of fitting data means that they're also more capable of overfitting that data, right? And now if you're not familiar with overfitting basically means that that the model looks at the data, and that data is comprised of some signal and some noise, okay? And and the model's job is to distinguish the noise from the signal. And overfitting is when it is mistaking some of the noise as signal. And the consequence of this is that when that model is then deployed on data on which it has not been previously trained, assuming that some of the noise is actually signal, it will look for, weird way of saying it, but it will look for that signal where it does not exist in this new data, right? And so it will have a harder time dealing with this new data, again, because it is looking for signal that is not there. It is looking for signal that was actually noise in the data that it was trained on. Okay, so so let's just go linear here. So in general, not in all cases, in general, especially normal linear models, more parameters makes the model more flexible, okay? And more flexible models overfit the data more, and therefore they should be penalized more, right? With something like, so with our information criteria. Now this connection between parameters and flexibility and penalization is directly seen in AIC, right? So in AIC, where's AIC? Here's our formula for AIC, and the P sub AIC is our penalty term for AIC. And what is that? It is simply the number of parameters, okay? And so in AIC, we see this very direct connection between the number of parameters and the penalization, okay? And again, for normal linear models, this is a, this tends to do very well in terms of assessing overfitting risk. So where are we here? Okay. But once we start to step outside of normal linear models, which the book is coming to very quickly, the connection between number of parameters and overfitting risk starts to decouple a little bit, okay? And then we realize that the number of parameters is really just kind of a surrogate for flexibility or for risk of overfitting, okay? But as that relationship starts to decouple, we should become more suspicious of penalizing the number of parameters. What we would really like to do is to penalize something closer to the risk of overfitting, right? More directly penalize the risk of overfitting, or more directly penalizing flexibility of the model. Okay, and that's what's happening, or that's what these different methods, PSIS, WAIC, and I guess cross-validation to an extent, that's what they are trying to do. They're trying to penalize based on something much more closely related to the flexibility of the model, okay, and the risk of overfitting of the model. I would guess then that the reason that we continue to call it effective number of parameters is just for continuity with AIC, which again is penalizing directly based on the number of parameters, okay? So the question then asks us to consider what's going to happen as our prior probability distribution becomes more concentrated, okay? And so we can think about that in terms of this more flexible, less flexible spectrum. So let's think about what happens if we make our prior distribution more concentrated. Does our model become more or less flexible? Okay, so again, if our prior distribution is more concentrated, is our model more or less flexible? Well, the flexibility is going to decrease, right? Because a more restrained prior distribution is going to narrow the values that our model will consider for estimation, right? So it's going to become less flexible. It's going to be less capable of fitting data, but also then less capable of overfitting the data. So a more concentrated prior should, in general, all else being equal, incur a smaller penalty, all right? And so now we've reasoned ourselves from understanding the effective number of parameters and the penalty of the PSIS to WAIC to trying to predict what's going to happen with a more concentrated prior, all right? So let's actually look at this with an experiment. And so we'll start by making some fake data. So I'm going to have 25 samples of X and Y, where X is a normal random variable with mean 0, standard deviation 1, and Y is a function of X. Namely, it's twice X plus some random noise here, okay? All right, and I've wrapped that together in a list, okay? And now I'm going to use two different models, one with a diffuse prior and one with a concentrated prior, but everything else being identical between the two models, okay? And so I have Y is normal with mean mu and standard deviation sigma, and mu is a function of X, and so it's beta X times X, okay, in both models. Now the diffuse model, the diffuse prior, has a wide standard deviation for beta X, okay, 10, and the concentrated prior model has a more concentrated prior, namely 1 for beta X. So the first thing that we'll do is we'll look at the summary outputs, okay, and then we'll look at how they compare with WAIC as well as PSIS, okay. So we run this, and so again, the top model here is the summary output for the diffuse prior, and then we have for the concentrated prior beneath. And we see, so just looking at our beta coefficient, okay, our estimate, it's pretty similar between the two models, okay, almost identical. But now, and that's fine, that's whatever it is, but remember the accuracy of the model does not describe its overfitting risk. Okay, these are two very different things, okay? And in fact, an overfit model, an overfit model is going to give you estimates, and you don't know whether those estimates are good or not, right? So we're running this additional analysis on our model to try to learn more things about our model, how generally applicable it is to other data, specifically other data from the same data generating process, okay? So I'm going to use the compare function, which is part of the Rethinking package. Which reminds me that if you haven't done so already, you need to make sure that you've installed and loaded the Rethinking package. So let's see here, okay? So I'm going to compare it, okay, using WAIC as well as PSIS, just for thoroughness, I suppose. Okay, so this is interesting. This is not what is expected, but this will happen depending on the data that we get at this draw. So I'm going to rerun this again. But notice here that despite our thought experiment, the more diffuse prior actually comes out as being the model less likely to overfit. Okay, so that's kind of interesting. Again, that is really just a function of the random data that we've generated. So I'm going to rerun this again. I'm going to pause this just to save some time on the video, but I'm going to rerun it all again and come back to this screen. Okay, so I've done so, and this time we have the more concentrated prior having a better score than the diffuse prior. And so if you want, you can take this code and rerun this several times. And in my doing so, generally the more concentrated prior is coming out with the better score, the less likely to overfit the data. But once in a while, you do get that the more diffuse one comes out better. And again, this is I think there might be an important lesson here, which is that all of these methods, we never have. It's really a beautiful philosophical point. we never have ground truth when we're doing these things, right? We are doing our best to estimate things that we do not know and have no reference to verify in some absolute sense. So anyway, but this is the expected outcome of this compare function, okay, is that the more concentrated prior has a lower overfitting risk, okay, and that aligns with our intuition. All right. Now, so what does this mean practically? Well, practically what this means is that our more concentrated prior should do a better job on data of predicting data that has not previously been seen. And so I want to see if we can do something that kind of tests that prediction, okay? So this is kind of an analog of that idea, but I'm going to use these exact same models, but this time y2, or I have a new outcome variable I'm calling y2, and it's more variable, it has a standard deviation of 10, whereas previously it just had a standard deviation of 1. So now remember that I said that one of the consequences of having a more diffuse prior or a more flexible prior is that it's more likely to confuse some of the noise, now we have more noise, as signal. Okay, so what I predict to happen here is that the concentrated prior is going to have a more accurate estimation than the diffuse prior of the actual relationship between x and y. In other words, the beta x from the concentrated prior, I'm predicting to be closer to 2 than the more diffuse prior. Okay, and again, all that's changed here is how diffuse or concentrated the prior is for beta x. Okay, so let me run this, and we have the summary outputs. Okay, so again, here we have for the more diffuse prior and for the more concentrated prior. And just as we predicted, the more concentrated prior is much closer to the actual value for beta x than the more diffuse one. And again, what's happening is that the more concentrated prior is less likely to mistake noise for signal. Okay, so so there's one more wrinkle in all of this. So ask yourself, are more concentrated priors always better than less concentrated priors? Okay, like in this case, that certainly seems to be the case. But of course the answer is no, right? Of course the answer is no, because we've actually cheated a little bit here, right? We have set the prior for beta x to center on the actual value of 2, okay? But again, we're usually trying to estimate this, right? Our prior is really, might be a guess, but but the fact that we have centered it on the actual value has kind of given a leg up to the more concentrated prior. So now we'll do this again, okay, with the same data, but now I've changed the priors. I've left diffuse standard deviation and the concentrated standard deviation the same, but now I'm centering that prior onto a different value other than the actual value of beta x, okay? And so now when I run this, sometime, let's try this again, okay. Okay, so we're going to ignore that. So because I suspect that it's the second model, but because the prior is so narrow and not centered on 2, it's having the QAP function is having trouble fitting the model. So let me just run this a few more times and see if we can't. Okay, so there we go. So now it apparently converged. Okay. Okay. So now in this scenario, it's not clear. They're both doing a poor job, but I think that the important point here is that the beta x is actually for the more concentrated model is now quite far away from the actual value, right? It should be close to 2, but it's not. And okay, so sorry. So I reran that a few times just to make sure that I wasn't fooling myself. But anyway, so we see that the beta x for the second model here is a lot farther away from 2 than it was in the previous model. But also notice, and this isn't the same in every run, but in most runs, that the beta x from the more permissive prior, the more diffuse prior, does get closer to the actual value, right? with the off-centered prior, and that's because it was allowed to explore more of the possibility space. Okay, and so in this case, the prediction from the first model, from the diffuse prior, does better. Okay, and I guess what else is kind of interesting is that if you run through this several times, the compare functions, you'll get more confusing results here. So in this, just in the first draw here, we had kind of confusing results where the concentrated prior is better with WAIC, but the diffuse prior does better with the second one. And again, we could rerun all of these several times and get kind of confusing outputs here. So again, this experiment is kind of fun to play with, just because you can start to see the limitations, especially of these information criteria and PSIS in terms of fitting and overfitting risk. But anyway, I better call it good there.